Okay, so we went over the calendar here. Everybody knows what is happening later this week. Let's take a look at the starter questions here. Of A or B, which would you rather graph? B? Really? Rational function has asymptotes? That's awesome if it is, okay? We've really developed a love for those rational functions and horizontal and vertical asymptotes and that sort of thing, okay? It's really not too bad. This would be a relatively easy one to do, okay? It is improper. You would have to do some long division to find the slanted asymptote, but again, if you've got a slanted asymptote, that actually helps in the long run. It's actually easier to graph the end result, okay? But most people, I think, would like to graph this one right here. It's just a polynomial. Each one has an x-intercept. So each of these factors produces an x-intercept. So this one has an x-intercept of 1, -2, 3. The multiplicity for each one of those is 1, so we know it crosses. And what does it look like? Looks like x cubed. So that means it starts down here. How many turning points can it have? Up to 2. Up to 2. Degree minus 1. So 3 minus 1 would be 2. So it probably looks something like that, and all we'd have to do is find the x-intercepts, which we've already got. We know it crosses each one of those. What's the other point that we'd probably want to label on that? What's it? The y-intercept. The y-intercept is pretty easy to find, because what do we plug in to get the y-intercept? A 0 for the x. So if I plugged a 0 in here, this is -1. A 0 in here, this is 2, and this is -3. So this would be -1 times 2. That'd be -2 times -3. That'd be +6 for the y-intercept. Okay, we've got 4 points on the graph right there. We know roughly what it looks like, so that'd be pretty easy to graph. Okay, quite a bit easier than graphing a rational function. But if you like these, that's awesome. Okay, so if we were going to solve this inequality right here, how do we solve inequalities? Just like you solve an equation, except for what? Who can give me the exceptions to that? Yeah, Shane?
Whenever you divide by a negative, you have to switch the...
Okay, whenever you divide by a negative, you have to switch the direction of the inequality. And what else? Multiply or divide by a negative. You have to switch the direction of the inequality. So if I'm solving this problem right here, the first thing I do is I'm just going to move the 4 to the other side. I'm going to do that by adding 4. Does adding change the direction? Not at all. So I've got a 2x greater than, this is a 14, and then I divide by 2. At each step, just think, am I multiplying or dividing by a negative? If you're not, you don't have to worry about it. So this is going to be x is greater than 7. There's the answer. That's an inequality. We could graph it. We could come up with it in inequality notation. You remember in 1010 how you had to write it in set builder notation? So you wrote things like this. You love that too? All right. That was Shane's favorite. Okay, let's solve this one right here. We'd move the 1 to the other side by subtracting. Does subtracting change it? Nope. So this is going to be x over -6. This is going to be less than or equal to, this is 4. And then I get rid of dividing by -6 by multiplying by -6. So I'll multiply by -6 on this side and multiply by -6 on this side. Again, what are we doing to solve the problem? We're multiplying by a negative. So we're going to switch the direction. So this is going to be x is greater than or equal to, and this would be a -24. Again, that's the inequality. We could graph it, write it in interval notation, and all that sort of stuff. Okay? All right. So section 4.5 is about solving polynomial and rational inequalities, which sounds pretty awful. It's actually, I mean, if you look at it, it's a lot more complicated than solving the two of these. Okay, but we're going to do it in kind of a graphic way. We're going to draw some pictures of what these look like, and then we're going to talk about, well, what part of the graph are we interested in based on this inequality? Okay, and that actually turns out to be pretty easy, and it's a really good use for the graphing skills that we've learned in Chapter 4. So let's take a quick look at this. I find that a lot of times students struggle with what these inequalities mean. I mean, they're pretty easy, but if I say y is greater than 0, well, you understand what that means, but what's the easiest way to describe something that's greater than 0? Yeah, positive. Let's just say it's positive. And if the y is greater than 0, okay, if we look at an xy axis, if the y is greater than 0, that means it's up here. What that means is it's above the x-axis. So if I say y or f of x is greater than 0, I'm saying it's above the x-axis. And that's what we've got right here. So if f of x is greater than 0, that means f of x is positive, and it means f of x is above the x-axis. What does this mean? F of x is less than 0.
Low.
Okay, it means it's negative, which means it's below the x-axis. Okay? And what does it mean if f of x is equal to 0? It means it is 0. Okay, it's not the denominator. Okay, so we don't have to worry about that. Okay, it means it is 0, which means it is on the x-axis. So if we're going to look at these graphically, and we're going to be talking about what y is y greater than 0? Is it less than 0? Is it equal to 0? It's a lot easier to keep in mind that if we're saying y is greater than 0, f of x is greater than 0, we're just talking about above the x-axis. If it's equal to 0, it's on the x-axis, and if it's less than 0, it's below the x-axis. So all we're going to be doing basically is looking at a graph and figuring out where, remember that question where? That's an x question. Where is it above the x-axis? Where is it below the x-axis? And where is it equal to the x-axis? Where is it on the x-axis? Okay? So let's take a look at the first problem. Okay, we're going to compare each function to 0. We're going to make sure of that. Most of them are set up so they're compared to 0 already, but we'll take a look at some on the back page that aren't. Okay, so here's a pretty simple example. This is what we looked at earlier up above. Pretty easy polynomial to graph. Okay, it looks like x cubed. All of these have a multiplicity of 1. It's got an x-intercept at 1, -2, and 3. So let's draw a quick sketch. Doesn't have to be perfect. The answer is not the graph. The answer is the information that comes from the graph. So this is going to be 1 right here, -2 right here, and 3 right here. And it crosses at each one of those. So again, that's -2, that's 1, and that's 3. Now, if it looks like x cubed, where does it start? Does it start up or start down?
Yeah.
Starts down. And we're going to cross, cross, and cross. So it looks something like this. You know, that's pretty quick, right? That could easily, just making that graph and labeling it could be a question on the test. Just for the heck of it. What was this point right here? 0, 6. Okay. It looks right. It starts down and ends up. It's got 2 turning points. It crosses the x-axis at the right place, and it crosses the y-axis at the right place. Okay. Now that's all well and good, and it's great that we can do that quickly. But the answer to the problem is not the graph. It's solving this inequality. And we want to know when this function is, whoops, it's a less than, isn't it? Less than or equal to 0. Less than or equal to 0. And we just got done talking about what less than means and what equal to means. If we're looking on a graph, what does less than mean? Where it's below the x-axis. So where is this below the x-axis, or because it's equal to, where is it below or on the x-axis? So where is this below or on the x-axis? Okay, that's the question. So if you've got a picture of what it looks like, that's pretty easy to figure out. It's below here and here, right? So let's just write down what it is. Where in terms of x's is it below? Okay, -infinity all the way to -2. Now it'll always be round around infinity. What about the -2? Do we do a square or round bracket? Okay, we're going to do a square bracket here because it's on the x-axis right there. We get to include that. If this were a strictly less than, we wouldn't include it. Okay, and then where is it below again? 1 to 3, and those are square brackets also. Okay. That right there is the answer. This is it. Okay? So, quick sketch, and there we go. Now, I want to point out 2 things, so everybody listen. Most of the assignment is very similar to this. This isn't the only way to solve these, but here are the two things I want to point out. I think graphing this and visualizing what it is, hey, am I looking for on the x-axis, below the x-axis, above the x-axis? That's a pretty easy thing to do. And it's a good review of our graphing skills. The other thing we want to keep in mind is we're solving an equation. The point of solving an equation is to get something that when you plug it in, it actually makes the equation true. Or in this case, the inequality true. So what this means is pick any point in here, any point in that interval and any point in that interval, plug it in, and it will be less than 0. So let's just, for the heck of it, let's take a point. Now you don't have to write this down, I just want you to watch. Okay? Would somebody pick a point in this little interval right here? Charles, what? 2 is a really easy point to plug in, right? So just watch. If I plug in a 2, this one right here is a positive 1. This one right here is a 4, and this one right here is a negative 1. What's 1 times 4 times negative 1? Negative 4. Is negative 4 less than 0? Absolutely. Okay? So it works just fine there. Okay. Any questions? Okay. So based on that little example that we just did, you can also solve these using something called a sign line. Now, if you think about it, all we're really interested in is what's the sign of the answer to this little thing right here? Is it positive, is it negative, or is it 0? We want the ones that are negative or 0 because we want them to be less than or equal to the x-axis, right? So what we could do is we could do this, okay? Let's see. So it says, use the zeros to separate the x-axis into intervals. Pick a number in each interval and plug it into the function. If the result is positive, the function is greater than 0. If the result is negative, then it's less than 0. Okay? So here's how we're going to do example number 1 a different way. We're going to find the x-intercepts for each one of these. Remember, this is a 1, this is a negative 2, and this is a 3. So here's negative 2, here's 1, and here's 3. So what these do is this divides the x-axis into 1, 2, 3, 4 little intervals. And what we're going to do is we're just going to pick a point in each one of them. Okay? So somebody want to pick a point that would be down here less than negative 2. Negative 3. Okay? Let's plug in a negative 3. If you plug in a negative 3, you get a negative 4 for the first one. You get a negative 1 for the second one. And you get negative 6. Everybody good there? 3 negatives make a negative. Now, do we really care that it's negative 24, or do we just care that it's negative? We mostly care that it's negative, because the negative 3 was just kind of like a test point. We could have picked negative 4 or negative 422 or something like that. It was just a test point. All of the numbers that you choose from negative 2 down this way, they will all produce a negative. So this next one, I'm going to do this a little bit differently. Watch. Somebody pick a number in between negative 2 and 1. Negative 1 or 0 is really easy, right? Let's plug in a 0. Now watch. I'm not going to write down the number. I'm just going to look at this and I'm going to write down the sign. If I plug in a 0, what's the sign of this factor? Negative. If I plug in a 0, what's the sign of this factor? 0 plus 2? Positive. 0 minus 3? Negative. Now, I don't really care about the numbers. What I care about is I've got a negative times a positive times a negative. 2 negatives make a positive. So this is positive. Pick a number in between 1 and 3. Let's plug in a 2. For this first one, if you put a 2 here, positive. Two plus 2 would be positive. 2 minus 3 would be negative. Only one negative, so this is negative. And then pick any number you want past 3. Pick 10 if you want. Pick 100 if you want. Whatever number makes it easy for you. So if I plug in 100, is this one positive or negative? Positive. 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 3 positives, still going to be positive. Okay, now we've got to come back here and we've got to think about this. We want these to be less than or equal to 0. Less than 0 is negative. Negative here. Negative here. So we'll just write down the answer. This would be from negative infinity all the way up to negative 2. Do we include the 2? We do. Start again at, right here, at 1, and go to 3. Okay? Now, this is a little bit more numeric and algebra. This is graphing. Which one do you like better? Graphing? I do too. I think it's quicker, it's a good workout of our skills, and I think it's easier to see. Okay? All right. Any questions? Okay, let's take a look at this one. This is a very easy problem. This just is x times x minus 3 greater than 0. What shape is that if we graph it? It's a parabola. Which way does it open? Yeah, looks like x squared, so it's going to open up. Where does it cross the x-axis? 0 and 3. So let's just graph this. 0, 1, 2, 3. Now, it's a parabola that opens up. That's kind of a crappy looking parabola, but not too bad. Do we really care exactly what the parabola looks like? Nope. Because the graph, the parabola itself is not the answer. It's just where is this greater than 0? What does that mean on the graph? What part of the graph are we looking for? The part that is positive, or a better way to describe it would be above the x-axis. So we want this part and this part. So, where, question about the x's, where is this above and where is this above? This is above from negative infinity all the way up until 0 and starting over at 3 and going to infinity. Okay, so those are the answers. Negative infinity all the way to 0. Oops. Round here. What about around 0? Square? Why square? What's the inequality? It's a greater than. This is just where is it above the x-axis, not where is it on the x-axis. So we don't count anything that's on or below the x-axis. So everything from here over to here is below or on. We only want above. So we open parentheses, okay, round, start again at 3, and go to infinity. Okay, that's the answer. Any questions? Sure? Okay, let's do this one right here. What did I say we normally compare these to? What's different about this one compared to this one, and the one up here? What are these all compared to? They're compared to 0. It's easier to compare to 0. That keeps our argument intact because 0 is the x-axis. Y equals 0 is the x-axis. So we need to compare to 0 if we're going to use this technique. So the first thing I'd do is I'd move this over. Everybody watch carefully. If I move this over, do I have to change the direction of that inequality? Do I have to flip it? Nope, because all I did is subtract 9x squared, right? Do we know what this graph looks like? Looks like x cubed. Like x cubed. 3x cubed if, yep, 3x cubed if we wanted to get technical. What's wrong with the way this is written? It's not what? It's not factored. So let's take out a 3x squared, and we'd be left with an x minus 3. Am I right about that? Okay, let's look at this picture right here. Okay, now, this is a good review of graphing. Since the graph isn't the answer to the problem, if you want to take a few shortcuts, that's fine. I'm going to verbally talk about these. Okay, but we'll just write down what we get on the graph. What's the x-intercept that comes from here? 0. What's its multiplicity? 2. Touch or cross? Okay, if it's odd, it's cross. If it's even, it's touch. So at 0, it's going to touch. We know it's going to touch right there. What's the 0 that comes from this factor? 3. So we'll go over 1, 2, 3. What's its multiplicity? 1. Touch or cross? That's going to be a cross. Okay, where does it start? Does it start up here or down here? Down here. So we're going to come up here. Keep in mind it's going to, what does it do here? Touch at the 0, cross right here. Okay? And again, that's 0 and that's 3 just as a reminder. Any questions there? Okay, take a look at this inequality. What part of the graph are we looking for based on this inequality? Where it's above. Strictly above, right? Not on, above. Where is the only place it's above? Right here. So the answer is, starting at 3, going to infinity. Round or square around the 3? Round. It's got to be round because remember, it has to be equal to in order for it to be on. Okay? What about this point right here? What about the 0? It's on. Okay? Don't include it. Okay? Now, what would change? Everybody ready? What would change if it were this? What if it were greater than or equal to? Okay, 2 things would happen. We'd have to have the square bracket. And what else? We'd have to include the 0. Okay? So x could be 0 because right there, at that point, it is right on the x-axis. Okay? Comes up, touches for just an instant, gets down below, and then starts being above. Yeah?
I was wondering, could you have a union? If you wrote like square bracket, 0, square bracket, and then union?
Oh, yeah, you could do that. So you could do 0,
Yeah.
union, 3 to infinity. You could. Yeah, that'd be fine. Any questions? Okay, flip the page over. Let's take a look at the interesting ones. Okay, on the first side of this paper, they were all polynomials. We love polynomials because they're nice and easy to graph. They're nice and smooth. They got a lot of nice features. Okay, they're based on power functions that we're pretty familiar with. They don't have any domain issues. You can plug in anything you want and you can get out anything you want, pretty much. Okay? But if we look at rational functions, we've got domain issues or the potential for domain issues. Okay? We can still look at the graphs of these and then we can compare them to 0, compare them to the x-axis. So let's take a look at this one right here. Are there any domain issues? Are there any numbers that we could say, hey, you know what? I know for a fact this number wouldn't work. Not on this one because the denominator's a 2. How about this one right here? Yeah, what would we have to throw out? We'd have to throw out a 0. Right from the get-go, if you've got a rational function, you want to look at it and you want to figure out what are the domain issues. I don't have any of them here. I got some there. So this problem right here actually is not too bad to solve. Okay? Everybody watch? I could graph this just as it is, and it would look like 1/2 x squared. Because if I multiplied these out, that would be an x squared on the top, divided by 2 would be 1/2 x squared. Looks like a parabola of some sort, right? Okay, but I'm solving an inequality. I solve inequalities just like I solve equations. So, so if you were in my 10-10 class, and even if you were in Mr. Price's class, he probably asked you this. Do you like solving equations with fractions in them? Nope. If you have an equation or an inequality, you can get rid of the fractions if you don't want to work with them. So here's what I'm going to do. I'm going to multiply both sides by 2. Now, the advantage here is I get rid of the denominator. I'm multiplying by a positive 2, so I don't have to change the direction. And what's 0 times 2 anyway? 0. We just made this. We considered any domain issues, and then we made it a problem like is on the front side. So I'm going to do this a little more quickly now. We know it looks like x squared. What's the x-intercept? 3. 1, 2, 3. What's the x-intercept? negative 2, 1, 2. Parabola that opens up, and the multiplicity is odd for each of these. Look at my crappy parabola. Does that matter? Nope, because it's not the graph that's the answer. We want to know where this graph is less than or equal to 0. What does that mean on our picture? Below or equal to, below or on. Okay? So let's write down the answer. The answer is we started at negative 2, stopped at 3, round or square? Going to be square. Okay. Any questions? Okay. Let's just check and make sure. We think that any number in between negative 2 and positive 3 would make that inequality true. Ken, can you pick a number between negative 2 and positive 3 for me? 0. Let's plug in a 0. If I plug in a 0, then the numerator is a negative 3, a positive 2, and the denominator is a 2. So I have a negative, I'll just cancel those, I get negative 3. Is negative 3 less than or equal to 0? Yep. Okay, it's less than, so it qualifies. Good there? Yeah.
Is that the y coordinate?
Yeah, well, that's the function value, yes. Okay, so it would actually cross the x-axis at 0, negative 3. Okay. Any questions there? Okay, I need you to watch because this is going to get just a little bit more complicated. I need you to think about this. It's easy to do, but I need you to think about why this works. Okay, so on this one, I just multiplied both sides by a 2, a positive 2. Does multiplying by a positive 2 change the direction of the inequality? Nope, so I kept it the same and I had this easy polynomial to graph. Everybody good there? Look at the structure of this problem right here. It is set up exactly the same as the one up above it, except for instead of a 2 in the denominator, it's got an x in the denominator. Now we could go to the trouble of graphing this rational equation, so we'd have asymptotes and all that sort of stuff, or we could do this. Didn't I just say if you're solving an inequality or an equation with fractions in it, do you have to work with fractions? No, you don't. Okay? So what we'd be tempted to do is to do the same thing we did here. Everybody watch? We'd be tempted to multiply by an x. But here's the problem. Do you know what x is? No. I don't know whether it's positive or negative. So maybe it's a negative 5, in which case I'm multiplying both sides by a negative, and what should I do with the inequality? Switch the directions. Maybe it's a positive 22. If I'm multiplying by a positive, I don't have to switch. So it's a little bit fuzzy here. Well, do I switch the direction or do I not? Well, we don't know, but we can change this so we can absolutely guarantee we don't have to switch the direction. We could make sure we're multiplying by a positive. We want to multiply by something that will cancel off an x, but we also want to make sure that we're multiplying by a positive. Any ideas? 2x, close, what? Yeah, let's multiply by x squared. Is x squared always positive? Yep. So, the cool part about this is, if I'm comparing to 0, what's 0 times x squared? Still 0. I can then cancel one of these x's with one on the bottom, and I get an x minus 3, and an x plus 2. Now, in one step, took a little bit of explaining, but in one step I got rid of the denominator, and I went from graphing a rational function to graphing a polynomial. And is that not an easy polynomial to graph? It is, isn't it? X intercept, right here, 0. X intercept, positive 3. X intercept, negative 2. Looks like x to the third. See what good practice this is? Starts where? Down or up? Starts down, and what's the multiplicity of each one of these? 1. Cross, cross, cross. Now, I've been yapping about this for about 5 minutes now, but we've now got a picture that's pretty easy to solve this. Since this says less than or equal to 0, don't say anything out loud, less than or equal to 0, you should know what part of the graph we're interested in here. If we say less than 0, that means below the x-axis. If we say equal to 0, that means on the x-axis. So we want everything that's below or on the x-axis. So that's this piece and this piece right here. So let's write down the answer. The answer is negative infinity all the way to negative 2. And then again from start up at 0 and go to 3. Okay, are there any questions there? Okay, does anybody want to point out something that this is an inequality? This is a rational expression, and sometimes with rational expressions you have domain issues. You can't plug in anything you want. What did we do at the very beginning? What number did we throw out? We know you can't use 0. We know for a fact you can't use 0. So this technique makes it easy to find an answer, but we need to come back here and we need to make sure, oh, hey, did we include this answer that we know we can't include? We did. How do we change that? Really easy. We're just going to change this and we're going to make this a round bracket rather than a square one, and that's it. Okay? Any questions? Yeah. No, because remember, the graph isn't the answer. It just helps us get the answer. If you wanted to do this, if you wanted to think about what this would have to look like, this actually has a vertical asymptote here. It hits the x-axis here, and it hits the x-axis here. So it's gonna look something like this. So notice this is above where that's above. This is below where that's below. This is above where that's above, and this is below where that's below. It's a more complicated graph, but you could do it that way also. Okay. All right. Any questions? Okay. Let's do the next one then. It's already compared to 0. Got that part taken care of. I really don't want to work with the x plus 3 in the denominator, but I do need to keep in mind, what number can I not use as an answer? Can't use a negative 3. Let's keep this in mind. Let's throw that out to begin with, but just keep it in mind from here on out. What am I going to multiply by to cancel off the denominator? X plus 3 quantity squared. I'll do that on both sides. And again, if you've done this right, the cool part is an x plus 3 cancels. So I'm left with x plus 3 times x minus 4. And then over on the other side, because it was a 0, 0 times whatever we multiplied both sides by is still 0. Look how quick that is. Looks like x squared crosses at negative 3 and positive 4. That's the worst parabola you'll ever see. But does it matter? Nope. Because it has the right shape. It's above and below in the right places. We want to know where this graph is. Strictly above. Just those pieces right there. So the answer is negative infinity all the way to negative 3. Union 4 to infinity. We look at this little tip here. If there aren't any square brackets, you don't even need to check this. If there are square brackets, you definitely want to check this. But what's the one number we know we can't use from the very beginning? Negative 3. Did we use it in the end? Nope. So no adjustments are needed. This right here is the answer to that problem. It's that quick. Okay. Any questions? Okay, let's keep going. See if we can finish this up. On this next problem right here, can somebody tell me something good about it and something not so good about it? John? It doesn't have domain issues. That's good. It's not completely factored. That's not so good. Anything else good about it? It's easy to factor. It's a polynomial. Okay, it's not a rational expression, so we're in good shape there. And the big thing is, it's already compared to 0. If it's not compared to 0, everything that we've talked about today doesn't work because we were always comparing it to 0. We were comparing it to the x-axis. So let's factor this real quickly. I take out an x. I'm left with an x squared plus 2x minus 3. That's still not factored completely. I'm looking for two numbers that multiply to be negative 3 that combine to be positive 2. So that's going to be x minus 3 and x plus 1. Did I do that right? It's got to be a plus 3 and a minus 1, right? Please don't get carried away on the assignment or on a test and think, oh, I've got this handled, I've got this figured out, and then make a silly mistake like factoring, okay? Zero, negative 3, positive 1. Chase, what does this look like? X to the third. So does that start down or start up? Starts down, and we're going to, what do we do at every one of these? Cross here, cross here, cross here. We're looking for strictly above. So that's going to be negative 3 to 0. Start again at 1 and go to infinity. And they're all round brackets, right? Okay, any questions? All right. Last couple of problems. This will be perfect. You have just enough time. Somebody tell me something not so nice about that. Shane.
It's not compared to 0.
It's not compared to 0. That's the first thing. What else? It's a rational function. It's a rational function. So this is going to be a little bit more of a pain, but still not too bad. The first thing we're going to do is we're going to move the 1. So this is going to be x plus 2 over x minus 4 minus 1 greater than 0. Now, if you want to graph this in this form, be my guest. That would be a little bit of a pain in the butt. We want to have one single rational expression over here. So what we're going to do is we're going to make this one single fraction, one single ratio. So I'm going to do that by combining these, adding these together. If I'm going to combine fractions, I need a common denominator. So I need an x minus 4 here and an x minus 4 there. That's still a negative 1, right? So this is going to be x plus 2. When we did these in 1010, you were probably warned. If you've got subtraction, please be very careful. Everybody gets this right. Everybody gets, hey, this is going to be a minus x. And then they just write down, oh, that's a minus 4. Is it a minus 4? Distributing 3, you get a minus x. Minus minus 4 is plus 4. The denominator is x minus 4, and we're still comparing that to 0. So the numerator, this is pretty cool. It's a 6, right? The denominator, x minus 4, and we want to know where that stuff is greater than or equal to 0. So at this point, this and this are equivalent problems. At this point, it's just like the stuff that we did up above. It's just like these guys up here, okay? So if you were going to solve this one right here, what's the first thing you'd want to do? Okay, we're gonna get rid of the denominator in just a second. Emily, what is it? If you're solving an inequality, you want to look at it and say, hey, is there anything I know I can't use from the beginning? And I know I can't use what? I can't use a 4. I know 4 can't be in my answers. Okay, you could see that at the beginning also. Now here's the cool part. Charles said we're going to get rid of the denominators. Check this out. I'm going to multiply by x minus 4 quantity squared on both sides. The other side is still a 0. This x minus 4 cancels with one of those, so this is what I'm graphing. Whoops. Any questions there? Can you tell me what this looks like? 6x minus 24. It's a line, right? What's the x-intercept? X-intercept is 4. And it's like 6x. 6x starts down here and goes like that, and it's going to cross at 1, 2, 3, 4. So it looks like this. Oh, we're not quite done. Okay, we want to know where this graph is above or on, right? So Samantha, what's the answer?
4 to infinity.
4 to infinity, round around infinity. What about the 4?
Front.
Why?
Because it can't equal 4.
Okay, so it says it can equal these two things, so this has to equal 0. But remember, we had a rational expression. We threw out 4 to begin with. So even though it looks like here we ought to have a square bracket, we use a round bracket, and there's the answer. Okay, any questions? Okay, let's look real quickly at this right here then. What's the domain of this? If we're going to take the square root of this polynomial, what can you not take the square root of? A negative, right? So whatever this is, 3x cubed plus 2x squared minus 3x has to be greater than or equal to 0. We can take the square root of 0. We can take the square root of a positive. We can't take the square root of a negative. So could you solve this? Could you solve where that's greater than or equal to 0? Didn't we just do that up here? Yeah. Okay, that's all it is. We want to know where we can find a square root for this. It's got two issues. We want to know where this is greater than 0, equal to 0. So we'd want to solve something like that. Could you do that? We just did a bunch of these today. What's one number that we know it couldn't be right now? Can't be -3. So you can throw out -3 to begin with and solve for where that's greater than or equal to 0. That will be the rest of it. Okay? All right. Any questions? All right. Have a great day. There's the assignment right there. Please get going on that. Please print off the review assignment.